Welcome everybody to our joint talk from nLIGHT and Aconity3D. Our talk is about enhanced laser powder bed fusion through AFX beam shaping observed with high performance thermography. What are we aiming at today? After a brief motivation, I'm going to show you the working principle of the AFX beam shaping and then hand over to Martin. He will show detailed analysis of printing results in Inconel and concluding with a summary and a vision. A freshly painted room and a 3D printed part. You could say it is a different task, but a same challenge. For both of this field, like standard tools have been established, these being a standard brush for painting the room and a standard single mode beam for printing the part. Both have their reason to being there for the very fine details that need to be covered in both of these parts, like the edges of a room and all these fine details in the part. But of course, each room and each part has like large areas that could be covered a lot faster. So in the painting industry, there has been revolutionary innovation through decades of research by bringing up the paint roller, through which you can easily cover these large areas. But up to today, most OEMs in powder bed fusion still use this standard small beam even to print the big areas. While there is a similar solution on which we're going to dive in today a little more, and these are ring-shaped beams, which obviously give you a much bigger area to process with. And of course, it would be ideal if you can just quickly switch in between the two while you print a part. And this is exactly what nLIGHT has been coming up with. A rapid tuning of the beam characteristics directly out of the fiber that is connected to the printing system. So what you see here is an animation which really depicts what's happening in real. That is like you can change from a single mode beam through several stages to a full donut shaped beam, like a ring shaped beam. And the companies that use these beams have found that each of these single indexes, as we call them, have great benefits for whatever specific part of the part that you're actually processing. And let me show you very briefly how this works, because it seems like something that could just be a vision, not really be real. A standard fiber laser, as it is used, consists of a resonator and an output fiber. The output fiber being a single mode fiber giving you that beam that everybody uses. And what we're working on in order to make this work differently is we replace the standard output fiber by a fiber that has both a 14 micron core and a 40 micron ring around it. As a second, we use a fiber with a similar design that allows the beam to be moved inside the fiber. And as a third, we need a perturbation mechanism that can work from outside to this fiber in order to have the following effect on the light that is injected to this fiber. By this perturbation from outside, we can make the light from the core exit to the ring of this fiber. And the effect is that, as you see here, the beam profiles as the output fiber, we can reach any distribution of the light between the core and the ring by just a very simple outside perturbation of the fiber, but the whole light is always in the fiber. That's why we call this flexible, all-in fiber ring beam shaping. And looking at again at the architecture of the overall fiber laser, it changed just very slightly. We have inside the laser enclosure this beam shaping module, very compact, very reliable, and this turns a standard fiber laser into an AFX programmable fiber laser, as we say. And at this point, I'm handing over to Martin, which will deep dive into what the actual application benefits in powder bed fusion are.
Thank you, Andreas, for the kind introduction. So we are a machine manufacturer at Aconity3D, and we got this new laser system, so we needed to check out what can we do with it, what will be the benefits. The first is, of course, the idea we can print bulky parts with a bigger ring shape, got a more stable melt pool, print mixed geometries, and switch inside of the geometry to the Gaussian mode or the ring mode or some modes between. And it was for us quite easy to implement that laser source into our machines because we are a configurable machine manufacturer. Means the AFX is now just an add-on to our machines, which are easily implemented as all other options like the preheating devices or different other laser sources or process monitoring systems. So what we have done with the laser will be shown in a close recap in the next slide, which we have shown last year. We have run a very big parameter study, printed several hundreds of samples out of nickel-based superalloy 718 to see how the ring shape is influencing our material, our process, and the properties of our parts. We have investigated the defocused Gaussian beam with the same outer diameter as the ring shape and one index in between, which has a 50% power in the core and 50% in the ring. This extensive parameter study led to very new results where we got differences in mechanical properties of our part and especially in the texture of the parts that we printed. And the main findings I will show in the next slide to catch you up with what we have done. So as the interim summary of our investigation, we have used these three indices of the laser. The Gaussian beam was defocused, and we have seen that we have slightly different material properties for the ring shape in comparison to the Gaussian mode. Especially in our elongation at break, we have seen that it's much more ductile than our standard Gaussian distribution. And we were thinking, where does that come from? And the only influence we have seen, or the only difference in our parts that we could see, was a different texture. So the grains of our of the index 6 printed parts with the ring shape are much more pronounced into the build direction, which led to that better properties. But these properties are not only pronounced in the build direction, but also in the other directions. Our idea where that comes from is that the melt pool of the ring shape is much shallower and flatter, and the direction of growth for the dendrites, it's upward the building direction, and they are not intersecting in every melt track. And the problem is we have still done this very extensive parameter study, and we still have the problem, which I will describe in the next slide, that the L-PBF process is quite complex. So we still need to investigate deep, try to find out what's really happening, what is causing the differences in evolving texture or mechanical properties and microstructures of our part. And this brings us to a new idea of how we can observe the process in a better way to maybe see directly in the process what is happening. Can we see any more understanding out of it to really see during the processing this is happening and our mechanical properties are resulting because of different other interactions. Shown here are all the influencing factors which we know, spot size, intensity distribution, preheating of the platform, so all the machine specified factors. And then there is the interaction zone of our process where a lot of different physical processes are happening which are not yet fully understood. And all this comes together in our material properties and part quality. And it's crucial to investigate this field in the middle to find out what really happens in the process, and to maybe save time and parameter studies for the further investigations of new materials or other intensity distributions as well. This is why we came up with the idea to use thermography as an observation method of our process. We know that it's very challenging, so we have very fast cooling range in up to 10.6 Kelvin per second, and small areas of interest, so we need a very high resolution of our small melt pool, and we got problems with different states of matter, so we have different emission coefficients. We have not only this, also the spatters and smoke, the disturbances in the process are very high. So this is why the determination of exact cooling rates and temperatures is still very challenging. And what we can see in the video, even with our very nice equipment, we come close to see how the melt pool is evolving and what kind of temperature range we are having. And we see we have one measuring point on our surface area of a simple cube sample, and we just expose every single vector and measuring the temperature distribution over time. So our idea was to get the cooling rates out of these measurements. But even with 4,000 frames per second, it's really hard to get these fast cooling rates determined by that measurement. Also, the emission coefficients are hard to determine, but what we could see here is that we have at least a reasonable range of temperature distribution. We have a bending of the curve at around 1600 Kelvin, which is quite close to our melting temperature of Aconite 718. So the ranges of the temperature are not fully wrong, in our opinion. But we still weren't able to really get these fast cooling rates. We don't have enough measuring points per second. Then we came up with the idea to use our pyrometric sensors, which are much faster. So we have done the same measurement to detect kind of cooling rates. The problem there is we don't have temperatures, we just have an emission coming to the pyrometric sensors, but at least it could help to determine kind of the qualitative cooling rates in emission per second instead of Kelvin per second. So what we've done is we have done the same experiment as with the tomography. We have one measurement point on the cube, and then we are exposing the complete surface area. So we see that red curve up and down for every single vector. We have run a polyfit around that, put the maximum peak of that, and zoomed into that vector, which is the closest vector to our measurement point, actually measuring exactly in the melt pool. And there we have located the fastest cooling rate and have done that to compare all the three indices to see if there are any difference in the cooling rates, which maybe are another reason for the different mechanical properties and the texture. Very interesting is that we do see differences very clear. So we have on the left side our index 0, our Gaussian beam, in the middle the 50-50 distribution, and on the right side the ring distribution. And we see that from left to right the cooling rate is a little bit lowered, but in the middle it's having a peak. So there's no clear correlation of that measurement with our part properties, which brings us in mind that really the texture and the direction of growth might be the main influencing factor of our new texture of the parts, and not any changes in the cooling rate and other precipitations of the material. But what the tomography comes up with, what we see then, where we can use it very good for, is the next. So we run the study with the ring and the Gaussian again, and changed a little bit the setup. So we have a wider area of view. We see on the top view the Gaussian beam, and on the bottom view the same process, just with the ring beam. And the benefit is here we see much less spatters for that ring, even in this qualitative view. And if we increase the frame rate, it's getting more clear that we have completely different formation of spatter, which can be very easily observed with the tomography. And on the next slide, with just a few hours of one of our engineers, we can see where this can be used for. So it can be used for quality monitoring. We can count the spatters and then put the qualify the spatters in size and track the spatters where they land. So for crucial application, it would be possible to use such a system for quality monitoring of crucial parts, maybe very high application in aerospace or medicine products. And this gives us the spatter area distribution of all the spatters we have monitored during the process. And to bring that all together, we have run this investigative study, and there we needed to come up with a possible use case, which we would like to show you now. So we came up with the idea of printing turbine blades out of the Inconel 718 and check if we really can adapt that to a real part, what we have seen. So we printed one component on the bottom with the index 0, in a mid-size with index 3, and then changed again the distribution to the index 6. We cut it out, some parts of this, and run again an analysis, and we could see that this approach really holds up in these real components. So it's possible to tailor your mechanical properties of your parts during one process and use different intensity distributions within one part to have the best mechanical properties for your load direction or for your load case. And if we bring that into a use case for production, it's always interesting to talk about costs and time of printing. So we put in a realistic evaluation scenario. So we have 9 blades on our mid-size system with a part volume of 58 cubic centimeters. It's just equipped with a single laser system to make the calculation more easier and to show how fast we can print just with a single laser. We compared 3 different parameter sets, our standard Gaussian one, and then 2 different parameter sets we have investigated with the AFX ring mode. But also used the Gaussian mode for the contours. So we have the same surface quality, nearly same part quality, but different things in time and cost. They are the 3 parameter set. What we've shown where we have used the different texture tuning and measured everything was the AFX50 parameter set, but we also got very good density and good results for even faster parameter set with double the layer thickness. For the calculation, we have used normal constants of the machine preparation of an hour and half an hour for the part extraction, 100 minutes for inertization, and the shielding gas cost. And to put that in a diagram, we see here that our standard process is around 70-hour printing time, and with the fastest parameter set, we can go down below 20-hour printing time, which is a time reduction of 80%. And even if we use just the AFX50 parameter set, which is better in mechanical properties than the standard one, it's definitely up to 50% faster. And if we put that in numbers, it would be around 70% faster than with our previous parameter set. So to put that all into a conclusion and an outlook, we have run a very broad process window. We've seen with that AFX laser that we got a wide stable processing window with the ring mode. The mechanical properties are easily influenced by changing the intensity distribution, and this has led to a change in texture, which changed the strength of the part. With the tomography, we can use it for quality checking and gain more process insight. There's still work in progress to try to get further insight into the process. And showing you a use case, we see a productivity increase while maintaining part quality during using that laser. And this is not where we can stop. If we think further, we have something which we can show you. It would be even possible not just using one laser with different intensity distribution. It would be also possible, like in this video, to use 2 lasers, one for melting, one for preheating, with different intensity distributions. So the variables are endless, And yeah, we are always searching for people trying to investigate all these possibilities. If you have any question, feel free to ask. Thank you for your attention.